handle. The wafers are scrubbed and the edges are rounded off and beveled to reduce chipping. The wafers are then ground smooth on both sides to obtain a consistent flatness and thickness from wafer to wafer. They are rinsed and etched in chemicals to remove surface contamination. The final polish is done on only one side of the wafer. The characteristic mirror-like luster is free from scratches and contamination. The wafers are measured for resistivity, which is a function of dopant concentration. They are inspected, packaged, and sent to fabrication areas where they will be made into integrated circuits. Meanwhile, teams of engineers work together to design circuits that will be fabricated on the wafer's surface. In this facility, over 100 specialists are often required to design the next generation of a microprocessor.
You can actually increase the number.
The organization of a design team corresponds to the organization of a completed chip.
Right now our iCache is like 32K.
So let's at least offer them an option which gives them the performance.
Computer architects, working at the highest level of abstraction, define the overall function of the chip. They establish the microarchitecture, which regulates the timing and sequences of instructions that tell a microprocessor what to do. The design is divided into areas that perform specific functions. Each unit is assigned a logic designer, who works at the logic level to create more detailed specifications and establish hardware needs. Each unit is further subdivided into functional blocks. Each block is assigned to a circuit designer who works at the transistor level.
Alignment shifter, and for this alignment shifter we should be picking.
The design becomes a maze of interconnected microscopic switches, known as transistors. These transistors turn on and off hundreds of millions of times per second, and in the process, either amplify incoming electrical signals or represent this information as a digital 0 or 1. These two states make up the code used in modern electronic communications. They are the logic or language that computers understand and translate into useful operations. To see how transistors work, let's examine a pair of CMOS complementary metal oxide semiconductor transistors. The N-channel transistor has two heavily doped electron-rich N-type regions, separated by an electron-poor P-type substrate. The electron-rich regions, called the source and drain, become the ends of an electronic switch, which is normally off. The gate electrode is close to, but electrically isolated from, the P-type region. The application of a small positive voltage creates a net positive charge on the gate. This charge attracts electrons from the drain and source regions, turning the switch on. When the gate voltage returns to 0, the transistor is again off. In a normally off P-channel transistor, heavily doped P-type regions are separated by a lightly doped N-type substrate. the application of a small negative voltage repels electrons but attracts the positive carriers, turning the switch on. It is possible to fabricate both P and N channel transistors on the same wafer by doping sections of the wafer. This is known as complementary MOS because a gate voltage which turns a P channel transistor on turns an N channel transistor off. To illustrate this complementary switching, a top view shows current flowing through the P channel transistor in the upper left. A voltage signal entering the gate electrode turns on the complementary N channel transistor, allowing charges to drain through. This opens the lower set of P channel transistors so the current flows through them. In this way, electrical signals can rapidly propagate through a complex maze of switches. Designing these circuits requires software and hardware tools like computer-aided design and computer-aided engineering. After circuit designers complete each block of circuitry, the computer checks for accuracy based on geometrical and electrical design rules. A mask designer takes the circuit schematic and manually lays out the channels in each layer of the mask and generates a master blueprint. These drawings are usually 400 or 500 times the actual size of the chip and enable engineers to visually check for errors.
Exactly the same clock, so you come in, tap, and then expand.
This information is electronically fed into a computer-controlled electron beam machine. In an ultra-clean environment, a fine electron beam will etch the patterns onto a series of chrome-plated glass plates. After the glass plates are etched, they become the masks that are used to transfer the circuit patterns onto the wafer. Each mask is inspected to ensure the patterns are good. The masks undergo a final wash in acids before they are carefully packaged.